Okay, so since everybody is here, maybe we can start again. So the second talk this morning is by Margare Bilu from Courant Institute, who will speak about Motivic Euler products.
Thank you very much. Thank you for the invitation. I apologize right away to people who have heard a similar talk before. I have included new things, so I hope you won't be too bored. The first thing I want to explain is what I mean by Motivic. When I say Motivic, I want to talk about the Grothendieck ring of varieties. So whenever K is a field, the Grothendieck ring of varieties is defined in the following way. As a group, it is the free abelian group generated by isomorphism classes of varieties over K quotiented out by the following relations. I want to be able, when I have a variety X, so X variety over K, I want to be able to cut it into pieces like this, when Z is a closed subscheme. So the class of X is always equal to the class of Z plus the class of the complement. There is also a product. If I have two classes in the Grothendieck ring, I can multiply them by taking the class of the product. So the unit element for this will be just the class of the point. And another important class is the class of the affine line over K. So in terms of this class, for example, we can have, so the class of the affine space of dimension n will be L to the n, and the class of the projective space of dimension n will be this funny geometric sum of ratio L. So this element L is a zero divisor in the Grothendieck ring of varieties. This is a result by Borisov. And therefore, we obtain it is a non-trivial operation to take the Grothendieck ring and invert L. We kill some elements by doing this. So this is a ring where we are mostly going to work in this ring, actually. And one last thing I want to mention about these Grothendieck rings is that there is also a relative version of Grothendieck rings. So we can consider a Grothendieck ring over some variety S just by replacing in this definition varieties over K by varieties over S. Okay, so now that we have, this is dangerous. Now that we have the definition of Grothendieck rings, I will, most of this talk will be, all the results in this talk will be about some convergence in this ring. So I have to introduce some topology, and the one that I'm going to introduce now is the one given by the dimensional filtration. Which is defined in the following way. So we have, for every D in Z, we define Fd of Mk to be the subgroup of mk generated by classes of the form the class of some variety times some affine space to the dimension minus n, where the dimension of x minus n is at most d. Okay, so this gives us a filtration of the Grothendieck ring, with L inverted, and using this we can define for every a in mk, we can define the dimension of a as the smallest d such that a is an fd. So for rational classes of varieties, this will be just the usual dimension of the variety, but for this it also makes sense of the dimension for other classes. And we have a filtration, so we can define the completion with respect to this filtration. So now most of the questions that I will look at are motivated by number theory, and I'm going to explain how. So there are many ring morphisms that we can define on the Grothendieck ring of varieties, and that will carry some geometric information about the classes of varieties. And the simplest one is the one that can be this one, which can be defined only when K is a finite field, and which is given by sending the class of a variety X to just the number of its points over the given finite field. And so whenever we have a question in number theory that involves some point counts of varieties, there may be some natural analog of this at the level of classes in the Grothendieck ring. And if there is such an analog, sometimes we can actually make sense of it even when the field is not finite and there is no counting measure. So this is what I mean by a Motivic analog of a number theoretic problem. So maybe one So one important example of this is Kapranov's zeta function. So again, if the field is finite and X is a variety over this field, then we know there is a zeta function associated to variety X. There are different definitions. The ones that I'm interested in are, there are different formulas. The ones that I'm interested in is the following. First of all, it is an Euler product over closed points of the variety X. And if we expand this Euler product, we get that it is the generating function of the number of zero cycles of degree n, effective zero cycles of degree n on X. And because of this expression, there is a natural Motivic analog to this function, which is defined in the following way. we take the generating function of the symmetric powers of the variety x, because the effective zero cycles of degree n are exactly the FQ rational points of Snx. So here Snx is defined to be x to the n, where I take the quotient by the natural permutation action on the coordinates. And so this makes sense for any field K. And there has to be some assumption on x so that this quotient is actually a variety. So for example, x quasi-projective. So this is a series with coefficients in the Grothendieck ring of varieties. Okay, so there are, since this function for x over a finite field, we know many things about it. One can ask which things are true for this function. So there are not that many properties actually go through. It is rational when x is a curve, but already for surfaces, most of the time it's not rational, even if we look at it in the localization MK. However, what I want to discuss now is the existence of an Euler product expansion. So this brings me to my second part, which is Motivic Euler product. So what is our aim here? My aim is to define Motivic Euler products in a general enough setting so that, in particular, I will get the expected Motivic Euler product for the Kapranov zeta function. So what is a general enough setting? So for now, let us take the following one. So K, a field. So I'm going to actually assume it algebraically closed here so that I don't have to bother with any degrees of points or anything, but the construction does work if K is not algebraically closed. X is a variety, quasi-projective variety over K. Everything should be quasi-projective because I will be taking quotients. And I also take curly X, a family of varieties over X. So it is important that they all come with a morphism to X. And I want to make sense of the following. Of such a product So why is this the most general thing that we could think of for now? Is that it's that I have a product over a variety of series where the coefficients vary algebraically in terms of a point in the variety. Okay, so these things here have to be thought of as the classes in the Grothendieck ring of the fibers of the different xi's. So I want to explain what this should be so that, in particular, Kapranov zeta function should be this thing, but when all coefficients are equal to 1, which is what we would get if we wrote down the Euler product there. Okay, so how does one do that? If we try expanding these things, this thing naively, what we see is that the contribution to, so if we expand so naively, what do we get? Well, the first coefficient is easy, it's 1. The second coefficient should be something like this. So sort of the sum of the fibers of x1 over all x. So it should be just the class of x1 in the Grothendieck ring, logically. And starting here, we have several contributions to each coefficient. Namely, we will have to the coefficient of degree n, we will have one contribution for every partition of the integer n. So what we're going to do is that we're going to construct the coefficients of this Motivic Euler product partition by partition. So we fix an integer n, at least one, and we fix a partition of n. Here, this is the number of occurrences of the integer I in the partition. Okay, so this means that sum of I times ni over I should be n. And I'm going to construct the contribution to the partition pi. So how do I do that? Well, partition pi means that I have chosen here the term of degree I in ni factors. So what I start with is xi, so the ni, and I take the product over all I. The other thing is that the different coefficients, these different things, I chose them in different factors. So if I look at the morphism to the same product but with xi replaced by x, which is given by the fact that the xi's are varieties over x, then here the image should actually lie in the complement of the diagonal. So this is complement of the diagonal, that is points with coordinates all distinct. So I restrict here, and so I restrict above too. And the last thing I need to do is notice that there are between factors where I chose the same term, there is no real difference, so I should take the quotient by the permutation action by this product of symmetric groups. And I do the same on the bottom. Okay, and so this thing here, I will denote it as pi curly x. So this is the symmetric product of the family curly x with respect to partition pi. And if we look at this construction, we see that here, this is actually the same thing, but just with when all the xi's are equal to x with the identity map. So this thing here will also have a particular role, and I call it S pi straight x. So definition, so this Motivic Euler product for now, I define it as a notation for the following series: sum over n and sum over pi partition of n of the class of S pi x for all partitions pi t to the n. So this is defined as a series with with coefficients in the Grothendieck ring of varieties. And this for now is just a notation, but let me give an example, which is the one I'm interested in above. So if xi equal to x for every I, then what we get here is the sum over all s pi straight x. And this actually is just the locally s pi x, if we look at it, it's just the locally closed subset of the symmetric power Snx that corresponds to effective zero cycles of degree n, the coefficients of which have partition pi, give the partition pi of n. So the sum over all these classes just by the cut and paste relation, which is this is exactly S and x, and so we do get Kapranow's zeta function here. So now that I've given this definition, there is still a lot of work to do to actually prove that this is not just good as a notation, but that this actually can help us make calculations with these Euler products, that most of natural operations that we would like to do with these products actually work out. So I'm not going to say much about this because it's rather technical, but one important thing for the things that I'm going to talk about later is that we can also make sense of these Euler products in more generally when the xi's are not actual varieties over x, but just some classes in the relative Grothendieck ring over x. So, let me just erase this. So when xi are sort of non-effective, so there might be just like some sum of classes, maybe with negative signs, then one can also make sense of this. So to explain this, let us go back to the definition here, and which is just above here, and notice that, so what I did is that, you remember there were sort of two steps. When I took this product, there were two steps. I restricted and then I took the quotient. But I could very well have taken the quotient first and then restricted to the appropriate subset. Okay, so S pi x is also equal to xi. To this thing here, so that some product of symmetric powers restricted to the image of the couplet of the diagonal in the product of symmetric powers of x. And so this shows us that as soon as we have explained what a symmetric power for such an element is, we know how to define this, because restriction will just be some operation between relevant Grothendieck rings. And so we just need to explain what a symmetric power of, so need to define as an ixi. And this relies on the following remark. If we have a symmetric power, let's say of a difference of two elements in the Grothendieck ring, then we would like it to satisfy the following pretty natural thing. Why should this be true? Well, in the case where here we have an actual variety, these are zero cycles of degree n on this variety, and we would like, if we restrict them on some subset, then we would like to get a zero cycle of some degree k, on the subset and zero cycle of degree n minus k on the complement. So it's pretty natural that we would like this to be satisfied. And so if we have this, we see that when y equals z, there is, using this, there is an inductive way of defining Sn of minus z. And once we have defined Sn of minus z, using this formula, we can define Sn of any element of the Grothendieck ring. But it relies on, like, the formula for it is more complicated. It is something, some big alternating sum of some configuration spaces. Okay, so this is all I wanted to say about Motivic Euler products. And so now I'm going to pass to applications. And the first application I want to give is to Motivic stabilization. And this is joint work in progress with Sean Howe. Okay, so as a motivation, let me first state a theorem which is due to Ravi Vakil and Melanie Wood from 2015, I think, which is the following. So X is a smooth projective variety over K. K is any field of pure dimension D. Dimension n. And I introduce the following notation for and L ample and bundle on X. And I introduce, so I'm interested in the space of sections of L to the D when D is large, and I introduce the following open subset. So these are the sections that are smooth. Okay. Then the statement of the theorem is the following. If I take the class in the Grothendieck ring of these smooth sections, and I divide by the class of all sections, so I'm sort of looking at the Motivic probability that the section is smooth. This does make sense in the Grothendieck ring localized at L, because this is just a vector space. Then this has a limit with respect to the dimensional filtration, which is the value of Kapranov's zeta function as at L to the minus n plus 1, where n was the dimension of the variety X. So this must ring a bell for many people here, because this is a Motivic analog of a theorem due to John Putins. So this is a Motivic analog of Putins' Bertini theorem over finite fields. Putins' result says basically this, but over a finite field. So Kapranov's zeta function is replaced by the zeta function of the variety X over the finite field, and L is replaced by Q, the number of points of the field. But the interesting thing is that this theorem doesn't imply, at least not to my knowledge, doesn't imply Putins theorem, because so I told you about the counting measure before, but actually we cannot just sort of specialize this theorem via the counting measure, because the counting measure is badly non-continuous with respect to the dimensional filtration. So there are like simple sequences, like if you take something like this, by the counting measure this is always 1, but the dimension of this goes to minus infinity. So it will be very small in the Grothendieck ring, but will be constant equal to 1 via the counting measure. So yeah, so these theorems are therefore, the proofs are pretty unrelated, and the theorems, none of those two theorems implies the other. Okay, so what I want to talk about is a generalization of this theorem. So in Putins' paper, there are a few generalizations to where you allow pretty general Taylor conditions actually on the varieties, on the sections, and this is what we do. We generalization to like more generalization to other Taylor conditions. So though Vakil-Wood's theorem can be stated and proved without Motivic Euler products, for this we actually really need Motivic Euler products. So what do I mean by a Taylor condition? So there is such a thing as the sheaf of principal parts of the line bundle L to the D, which corresponds to the degree m Taylor expansions of the sections of the line bundle. And so when this inside here is a vector bundle, and this principal part sheaf is a vector bundle over X of rank n plus m choose n, which I denote by n index m. And what I mean by a Taylor condition will be therefore just a constructible subset of this sheaf of principal parts. So I'm just choosing among all of these Taylor conditions at every point, I'm just choosing some. And I need to make some restrictions on U. So there will be actually, I won't write it down because it's a bit lengthy to write down, but there is a condition so that on the codimension of the complement of U. So the codimension or the complement of U should be sort of big enough. So the complement of U should be small enough. U should involve most of the elements in here. So maybe one special case that I can write down so that it's clear what I mean is, for example, it works if the codimension of U complement is at least n plus 1, where n is the dimension of the variety. Up to a finite number of points. We can remove a finite number of fibers. Okay, so if we have this, then I have the following theorem. So for any m, so m is the order of Taylor expansions that I'm looking at. So once I fix the order of the Taylor expansions, and then there exists epsilon, some positive epsilon, such that for all U as above, so for all possible Taylor conditions inside this thing, we have the following. So if we introduce this notation as the sections such that the Taylor expansion of f at every x is in U. Then, as for Vauquelin-Wood's result, if we take this Motivic density, then we can write the following. So here I'm not going to write this as a limit because you can notice that my U here a priori depends on D, so I should fix compatible choices of U's for different D's, which here is done automatically because I just say I take the smooth ones, but here what I'm going to do is that I don't choose anything like this, but therefore what I will have is some equality here with a big O. So what is the Motivic probability? Well, the way I write it down is like this. So it's an Euler product with just one coefficient, which is minus the class of U. And I evaluate it at L to the minus the rank of the bundle of principal parts. And so here is the complement of U. Okay, so if you do the computation formally, you will see that each factor should be just equal to Ux over L to the nm. So is a Motivic probability that the given Taylor expansion at X is in U. Plus big O of L to the minus epsilon D, by which I mean that it is equal to L minus integral part of epsilon D times something bounded for the dimensional filtration. So the Vauquelin-Wood's theorem, the proof relies on some kind of Motivic inclusion-exclusion principle. So they write it, they don't name it like this. I think the term Motivic inclusion-exclusion is actually due to Shan. And what's nice is that their proof essentially goes through once we understand well how these Motivic Euler products with these non-effective coefficients behave. So once we have this Motivic inclusion-exclusion has actually a very nice compatibility with these Motivic Euler products. So the proof essentially goes through. But so one other thing that I want to mention is that we have we actually generalize this. So there's a generalization that is possible to sections of X where I have not only a line bundle, but I twist the line bundle by some coherent sheaf. Okay. And this again, it's not much more complicated per se. It's just that when we have this additional coherent sheaf, then the bundle of principal parts is not a vector bundle anymore, and we have to pass through a flattening stratification to make it into a vector bundle. So it's more technical. We have to stratify things, but because we are in the Grothendieck ring of varieties, stratifications usually don't affect the end result. And the nice thing with this is that this gives us this is sort of the right setup to get Motivic analogues of many variants and generalizations of Putins' Bertini theorem that are present in the literature. So the first thing is sections containing a fixed subscheme. Okay, so here we'll just take the ideal sheaf of the given subscheme. So this in the arithmetic setting, this is due to first Putins, who did the case where the subscheme is smooth, and then to Günther. There's also complete intersections. So instead of having just one hypersurface, we have actually a complete intersection where all degrees go to infinity. This, in the arithmetic setting, is due to Bucor and Kedlaya. And the last thing is semi-ample Bettini. So this is due to Ehrman and Wood over finite fields. Okay. So yeah, this is pretty promising, and we hope to find other nice motivic stabilization results, and we hope that they will motivate maybe then some more topological results about stabilization of cohomology of some of these spaces. Oh, I'm sorry. Okay, so now I'm going to go back to the topic of this conference, which is rational points on Fano and similar varieties. And so I'm going to give an application to a motivic analog of Manin's conjecture. And this was originally the reason why I defined these motivic Euler products. Okay, so there's a pretty lengthy geometric setting, which I'm going to give now. So the base field here is algebraically closed of characteristic 0. C is a smooth projective connected curve over K. I denote by F its function field. And I take pi from curly x, script x, to C a non-constant morphism. Yeah, here x is a smooth projective variety over K. And I also give myself L, a line bundle on X. And I will make assumptions, and the assumptions will be not on script X and script L, but on their generic fibers. So I define X to be straight X to be the generic fiber of script X, and straight L to be the restriction of L to straight X. Okay, so what I want to give here are my assumptions, which are my generic assumptions. So the most important one is the first one, which is a structural assumption on straight X. So X is an equivariant compactification of the additive group of dimension n. That is, X has an open subset isomorphic to G. That's the compactification part, and the equivariant part is that, and the addition law on G extends to an action on an action of G on X. So it's this sort of the additive version of toric varieties. The other thing is that so I have an open subset inside G, and I want this to be a divisor with strict normal crossings. A strict normal crossings divisor. And the last thing is an assumption on the line bundle. So the aim is to sort of count rational points of bounded height with respect to L, and this usually works the best if we pick L to be the anti-canonical line bundle here. So these are my assumptions, and now I'm going to, what do I want to do with this? Well, I'm going to look at the following space. I'm going to look at sections sigma from, so sigma are sections of this pi over there, and there are two assumptions on them. The first one is some assumption on the degree. So when I say the degree, I mean the degree with respect to my given line bundle. So this should be of degree D. And also, I want them to send the generic point of C into the open subset G, so that they correspond to rational points on G. Okay, so the picture is the following. I have X here with some things at infinity. Here is C, and I'm looking at sections of like this that exit G only at a finite number of points. So this exists as a quasi-projective K-scheme by the theory of Hilbert schemes, and therefore I can consider what we call the Motivic height zeta function, which is a generating function of these things, and ask about its convergence, and this will give me some results on the growth of these MDs. So let me maybe give you right away. No, let me first, so I will state now the theorem that I have, and the only thing is that I have to define, I will say that zeta converges with respect to some topology, but it won't be the dimensional topology that I talked about earlier. So it is a topology that's defined in a similar fashion, but it's a bit finer. But I'm going to explain this just right after. Okay, so this topology is defined over C, so that's why for this theorem I am assuming K equals C. And I put R to be the rank of the Picard group of X. Then there exists an integer A, at least one, and a real number delta, positive, such that my zeta function, if I multiply it by LT to the A, and this to the power of the rank of the Picard group, converges for T smaller than L to the minus 1 plus delta, and takes a non-zero effective value at L minus 1. No, that's not what I want. So I'm going to tell you right away what the, not completely right away, but soon, what the topology is. But first of all, I want to give you a corollary just to convince you that this gives a lot of information. So by some Lefschetz principle type argument, we can actually here get rid of the assumption k equals c. And we will get the following result for growth of MD. Because of this integer a here, we won't get a result whenever d goes to infinity, but we have to restrict to congruence classes modulo a. So for every p, for every congruence class between 0 and a minus 1, one of the following occur when d goes to infinity in the congruent class of p mod a. So there's two cases. The first one is the less interesting one, which is that dimension of md minus d goes to minus infinity. So this includes in particular the case when all the MDs in some congruent class are empty, which might very well happen. So this is the less interesting part. But what also might happen is that actually dimension of MD minus D converges to some constant, to some finite constant. So this means that eventually MD is just, dimension of MD is just equal to D plus some constant. And I can also say something about the number of irreducible components of maximal dimension. Namely, this number will be, for d sufficiently large, will be a polynomial in D of degree at most r minus 1. And yeah, I told you that the second case is more interesting, and fortunately it actually sometimes happens. So moreover, the second case happens for at least one value of p. Okay, so this is a statement, so I hope this convinces you that we can actually recover a lot of information. Actually, we can even, so kappa of MD is the dominant coefficient of the Hodge-Deligne polynomial of MD, and actually we can even get a positive proportion of a coefficient of the Hodge-Lewin polynomial, which will also satisfy this, be a polynomial of degree at most r minus 1. Okay, so I want to say something about the proof in the last 5 minutes. So for this, I need to first say that, so this is, there are some previous results. So in the Motivic setting, there's a result by Jean-Berlois and Leuser, which do actually, the setting is essentially the same, but they do S integral points. So the sections can only exit the number, the open set in a fixed number of points, S integral. And in the arithmetic setting, this is a Motivic analog of work of Jean-Berlois and Cinque. And how does the proof of this go? The proof goes, it's a pretty well-known principle. You take the height zeta function, you apply the Poisson formula to it, and this rewrites it in a way so that the term corresponding to the trivial character is the one carrying this pole of order r. And to prove it, you decompose it into local factors and you analyze each factor separately. And so the same kind of method works here, except that in the Motivic setting, we have no Poisson formula, and well, the decomposition into local factors is what is given by these Motivic Euler products. So you need, so for the proof of our result, you need Motivic Euler products. And this explains, so this is why Jean-Berlois and Leuser treated the S integral case, because in the S integral case, all products are actually finite. They just support it over the finite number of points. So they didn't need Motivic Euler products. You need a Motivic Poisson formula. And this is due to Hrushevsky and Kazhdan. And so in this case, one can apply it as is, but in our case, because the poles of the sections vary, we actually have to extend it a little to be able to apply it in families. And the main feature of this is that one has to introduce a bigger Grothendieck ring, which is the ring of varieties with exponentials over K. This is the ring needed to make such a Poisson formula work. And so the last thing I want to talk about in the last 3 minutes is the topology. This is not needed in this case, again, because the functions are rational. So one just describes the denominators and one doesn't need to talk about topology. So what's with this topology? Why doesn't the dimensional filtration work? Well, the reason lies in Jean-Berlois and Cinque's calculations for the local factors of this Fourier expansion of the height zeta function. When they estimate the local factors, they end up with having to bound. So this is these are some boundary divisor. And they end up, in every local factor, they reduce to the residue field, and they end up having to bound something of this form, some difference like this, okay? And this they do by Langbail estimates. So this is bounded by some constant times n minus 3/2, which is n minus 1, which is the dimension of these two things, minus an extra 1/2, which they gain by these Langbail estimates. So the calculations in the Motivic setting are completely analogous. So what do we end up with? We end up with a class of this boundary divisor d alpha in the Grothendieck ring minus L to the n minus 1. And if you apply the dimensional filtration to this, the only thing we can say is that the dimension is smaller than, is at most n minus 1, but we cannot, in general, we cannot say anything more. So this is not enough, and we need something a bit better. We need to gain this 1/2. And to do this, we introduce the following. So this is why we need k equals c here. I mean, we need it at least in the way I constructed it. So there is what we call a universal Hodge characteristic, which is, this is the Grothendieck ring of Hodge structures. Just defined pretty naturally. And whenever I have x smooth projective variety, I'll only define for smooth projective because that's when it's easier to write out. I associate to it the alternating sum of the classes of the Hodge structures that I can put on the singular cohomology of x. Okay, so this is well defined because this is actually generated by smooth projective varieties. And on this ring here, I can filter it by weight in the same way as I can filter the Grothendieck ring by dimension. So here, there is a weight function going to z, which I can pull back and get a notion of weight on the Grothendieck ring of varieties. And so then I can define the radius of convergence whenever I have a series with coefficients in the Grothendieck ring of varieties. I can define the radius of convergence of f to be the lim sup of the weight of the coefficients divided by 2i, 2 because the weight of the affine line is 2. And I can say that whenever S is at least sigma f, I can say that f converges for t at most L to the minus S. So this is how this convergence that is used in the statement of the theorem that I already erased works. So I think I'm going to stop here. Thank you.
Okay, thank you. So any question or remark? Okay.
Okay, I have a couple kind of related questions. In your and Sean's stabilization thing, the big O, does the proof give any control over like the complexity of those things, like beyond the dimension?
So you mean like what the epsilon is, or what the?
No, I guess maybe like how many, like you have the dimension, you have it's like that your product plus some extra terms whose dimension isn't too big. But like say, I mean, if you wanted to hope to specialize somehow to a finite field counting thing, you would say that if you know there weren't that too many of those.
So let me think. I mean, I think essentially it's just, it's just the error terms that we get in the Motivic inclusion-exclusion. Yeah. So if you know those, then there's a bunch of them, right?
Okay, yeah. So okay. And the second one, I guess it's also like a complexity controlling thing. Like in the MD, you have the dimension behaves like what you would want it to be for the like Manin conjecture equivalence. If you like wanted it to be super specific, you would want them to basically have about q to the d points if you were over a finite field. And so you would again want that maybe like their degrees weren't like the Lang-Vey estimate would say it was pretty close to q to the dimension of the thing points.
Sorry, what was
sorry,
the question?
In the MD, that space of sections,
Yeah.
Do you have some kind of a priori control over like how complicated that set can be? Like outside of its dimension in terms of like its degree under some embedding or?
Oh, no, but I mean, as I said, I know a lot about like a bunch of the coefficients of the Hodge-Deligne polynomial. So for example, you see that I know things about the number of reducible components of maximal dimension. So there is some control over like the main terms of the Hodge-Deligne polynomial, which I guess are the ones that control the big things in the variety.
Cool, thanks.
I think there was, yeah.
So do you think that this does converge for in the original topology and just the method can't prove it, or do you think that it doesn't converge in the original topology?
I think it doesn't, but of course, like yeah, I can only give this argument. Yeah, I guess, yeah.
Yeah, actually, could you just say what happens to the open varieties when you look at this map to K0 of HS?
Sorry?
The map which you described from K0 of varieties to K0 of HS. So for open varieties, what do you associate?
Oh, then there's, I mean, it's just that there's going to be a, this is not a pure Hodge structure, but there's a Hodge filtration. It's just that it's going to be a bit, the definition is going to be more complicated, it's going to be a graded part. But it's, I mean, if I write it down, I'll get it wrong. But there's it will just we'll have like an extra sum here over graded parts of the filtration.
Suffices to describe it only for your smooth varieties.
Yeah, because the Grothendieck ring of varieties is generated by just smooth projective varieties.
And the complements K minus X minus some subscheme, right? So you have some open varieties.
It's then because of the cut and paste, okay. I can get all of them just by subtracting the closed subschemes. Yeah.
More questions?
Yeah. So yeah, I cheated a little, and because I explained to you how to define my topology on the Grothendieck ring of varieties, but I also told you that the Motivic Poisson formula works, it needs a bigger Grothendieck ring, which is the Grothendieck ring of varieties with exponentials. So I actually need a topology on this bigger ring. And well, I cannot, because I didn't define what this big ring is, I cannot really tell you much, but the idea is that there is a Motivic, there is a morphism which is called Motivic, which is given by the Motivic vanishing cycles, which are an object, the definition of which is due to Denef and Lezer. And I sort of take the sum of those, and this gives some morphism to the Grothendieck ring MK, but with some extra action of the roots of unity. So mu hat is the projective limit of all groups of roots of unity, and then I actually need a more general version of this Euler of this Hodge characteristic that goes into Hodge structures with monodromy. So yeah, there's some extra machinery that I sort of swept onto the carpet, but you can also define the weight filtration on this, and and that's the way things actually work. But I don't need this to state the theorem because the zeta function has coefficients in the original Grothendieck MK, Grothendieck ring MK. Just that to do the proof, I actually need this extra stuff.
Okay, any more questions? No, apparently not. So thank you again.